on Monday, we introduced these multidimensional periodic problems. Okay, that essentially had this sort of periodic substructure where, for instance, we have a cell here, and over this cell of heights P2 and width P1, we have some periodic conduction tensor such that, for instance, dx of y is periodic in y according to some vector yp. So for instance, we can look at a simple case that I wrote down, which would just be some constant plus cosine of 2y1 minus 3y2, such that yp is equal to pi and 2 pi over 3. So this is just, how you get from the bottom left corner up to the top right corner of the cell. So this added periodicity, it certainly makes things a bit easier because we can project a problem in an arbitrary domain to just this single cell here. Okay, and if we integrate over the microstructure on this periodic interval, then we can essentially average out the effects of the conduction tensor. So what we did to homogenize in this case was that we said, of course, y equals x over epsilon, and we converted our gradient to now a total gradient in x plus 1 over the gradient with respect to y. We substituted it into the PDE, and we also expanded out according to a regular perturbation expansion. And we're going to go up to order epsilon squared in order to find our homogenized problem. Okay. And so we found that for, let me just write down the original PDE, right? We have the divergence of dxy gradient of u is equal to f of x, right? And x is living on some domain omega that's inside of Rn. And you have some boundary condition g of x along the boundary, okay? And we assume that dx x over epsilon is positive and smooth, right? And we already wrote down the periodicity condition, okay? So what we found in our hierarchy is that to order 1, we have the gradient of y gradient with respect, divergence with respect to y, d gradient and y u0 is equal to 0. And we found that u0 is just going to be a function of x in order for it to be bounded, okay? So the key here with all of this typically is that we're requiring a bounded solution, so we're going to eliminate terms that just depend on y or y squared, because as we leave the micro scale, we're going to have to take y to infinity, and that would cause those terms to blow up. Okay, so at order epsilon, we again have the same operator, divergence d gradient of u1 is equal to now some inhomogeneous part, gradient d dotted with the x gradient of u0. And because u1 is periodic in y, we can solve the above in just the cell, okay, omega p. We did this, okay, and we also found that by superposition, and a boundedness condition, we have that u1 is equal to a dotted with grad x u0 plus c of x. C of x, oh, that's a weird parenthesis there. Okay, and with a periodic, okay, in y, and we also have that the divergence of d gradient of yai is equal to minus dyi d, okay, for y living in our cell, okay. So the next thing we got to was the order epsilon squared equation, okay, and we basically average this over a cell omega p, okay, and we applied the divergence theorem, and using our equation for u1, okay, we could further reduce, okay. So the full equation, which I wrote down last time, is divergence over y d gradient y u2 plus gradient x u1 plus divergence over x d gradient y u1 plus gradient over x u0, and make sure I have enough parentheses, and then we have this inhomogeneity f of x, okay. So the averaging over this is going to give us 1 over the volume of the cell, okay. The divergence theorem, remember we applied that. That's going to give us this normal derivative, the flux out of this domain, okay. And then for the second term, within it, we're going to have this average, which we can write as d dyi a dotted with gradient with respect to x u0 average over p. This is equal to average of dyi a averaged over the cell dotted with the gradient of x u0, right? Because this is not defined over the micro scale, so we can pull it out of an average that we're taking over the y variable because we're treating it as a multiple scales problem. Okay, so similarly, we can take this second term here and we can average that over our cell. Okay, and so similarly, the average of dxi u0 over the cell, right? This whole thing here, it just depends on x. So the only thing that depends on y is going to be d. So then again, we get this average over the cell, d average over the cell, omega p, and we just pull out the dxi term, okay? So all of this together implies that the average over the gradient, the divergence over x, d gradient over x u0 average with respect to p is equal to the divergence, and then we can just pass that average only along to d itself, okay? Because everything else just depends on x. So this method of multiple scales allows us to pull the x parts through, okay? So now if we combine and we average our order epsilon squared equation, what we get is the divergence over x of the average of dy a, sorry, gradient with respect to y of a, averaged over p dotted with gradient of x u0, plus the gradient with respect to x of average of dp gradient of x u0, and this is equal to f of x because that doesn't depend on y at all either, okay? So let's rewrite this more compactly, and we'll see what we finally have is the divergence over x of d, and I'm going to draw two bars under it, so I'm defining something new there. Gradient over x of u0 is equal to f of x, okay, for x in omega. So what do we have now? Okay, we have that u0 also on the boundary, okay, is equal to g. And what is this d thing? This is now our homogenized diffusion coefficient, which is just going to be the average of our original d gradient over y a p plus average of d over p, okay? So so in R2, our homogenized coefficients are going to be d, which is equal to d averaged over p d dy1 a1 p average over d dy1 a2 p d dy2 a1 p, and then dp plus dy2 a2 averaged over p. Okay. So we have this matrix now. It's a matrix of diffusion, homogenized diffusion coefficients. It's going to multiply through this gradient term here, and then you're going to take the divergence over that. Okay. And I can fit this in here. The divergence over y of d gradient y ai is equal to minus dyi d, okay, for y living in the cell here. Okay. So the periodicity basically allows us to say, well, I only need to focus on one cell. That's the average that I take this over, and then that average just sort of repeats itself throughout the domain. You now fill the domain now with these cell averages, and that's what's going to give you your homogenized coefficient that now only depends on the macro structure. Okay. So just to zoom out a little bit, what we've done now is just in multiple coordinates, right? I mean, I wrote down this example here at the bottom for R2, but this applies to R3 or, even more dimensions if you like. Okay. The idea is that at some point you have to take an average over your microstructure, and the key is to do that to the equation itself and see what that tells you about the effective diffusion coefficient. It's not enough just to average the diffusion coefficient itself, because you could get a very wrong and sort of inaccurate estimate of what the effective diffusion coefficient is, right? If we just done that, we only would have gotten these on diagonal terms, okay? And we wouldn't have gotten these off diagonal terms and these other corrections, okay? Which are going to depend on this variable a here, which has its own, let's see, did I go back to it? Yeah, which has its own partial differential equation that you have to solve. Okay, so it's by averaging the actual equation that you reveal sort of the proper homogenization of the diffusion coefficient. Okay. All right, so let me do this in an example, and then I'll be done. Okay, so let's consider a cell in 2D. Okay, omega p is equal to the intervals from 0 to a crossed with the interval from 0 to b in R2. Okay. And now to determine the homogenized coefficient, the under bar twice, okay, we have to solve for our AIs there, okay? And let's make some assumption on D, okay? Won't be too specific. So we'll have some arbitrary function of the macro structure, because remember, we're still allowing that to vary. But then we have some microstructure, e to the alpha of y1 and e to the beta of y2. Okay, so we're just allowing for separability maybe of the microstructure's diffusion coefficient dependence. Okay, so where alpha y1 and beta of y2 are periodic, okay, with A and B respectively, okay? And dy1 now of dy1 a1 plus dy2 dy2 a1 is equal to minus dy1 of d. And then we're going to have dy2 dy2 a2 plus the term dy2 d. Sorry, that should be a y1. Okay. And yeah, this up here should be a dy1, and then we have a dy2 a2. This is equal to minus dy2 d. Okay. All right. So this implies that e to the alpha y1 dy1 a1 is equal to something we'll call kappa 1 minus e to the alpha y1, and then e to the beta y2 dy2 a2 is equal to kappa 2 minus e to the beta y2. And then we can solve for these a's. So we get a1 y1 is equal to minus y1 plus kappa 1 integral from 0 to y1 e to the minus alpha of s ds. And then a2 of y2 is equal to minus y2 plus kappa 2 integral from 0 to y2 e to the minus beta of s ds. Okay. And by periodicity, okay, we have that a1 of 0 is equal to a1 of a, and a2 of 0 is equal to a2 of b. Okay, so we can apply that to these above formulas, and we get that kappa 1 equals a times the integral from 0 to a e to the minus alpha of s ds to the minus 1. And we have that kappa 2 is equal to b integral from 0 to b e to the minus beta of s ds to the minus 1. Okay, so whereas before we got this from sort of a boundedness condition when we weren't dealing with the periodic case, but sort of leaving the microstructure case. But here we have periodicity within the cell, and so we're essentially using that in order to specify our constants here in our equation. Okay, so now we have these A's, which we can use in our formula for the effective diffusion coefficient. And now since dy2 of a1 equals dy1 of a2 equals 0, so we don't have any cross terms owing to that separability, it follows that d12 and d21 are equal to 0. So we really are just going to have those diagonal terms along that matrix in this case. And now we can work out dy1 a1 average over p. So remember that that shows up here, right, in this on diagonal term, and then corresponding term here shows up for A2. Okay, so it's a separability that means that we're not going to have these cross terms here in this diffusion matrix. So this just requires a few steps to compute this integral, right? So we get 1 over AB, and then we're going to have a double integral since our cell is two-dimensional. So we have d0 of x, that sort of macro structure there, e to the alpha y1 plus beta of y2 times minus 1 plus kappa 1 e to the minus alpha y1, integrate with respect to y2, I guess, and dy1. Okay. We get that this is equal to minus 1 over ab, integral from 0 to a, integral from 0 to b, d0 of x e to the alpha of y1 plus beta y2 dy2 dy1 plus 1 over ab, integral from 0 to a, integral from 0 to b, d0x kappa 1 e to the beta of y2 dy2 dy1. Okay, so we get this is equal to minus actually just the average over d plus d0, which is going to pass through kappa 1 over b, integral from 0 to b e to the beta s ds. Okay, which really is just minus the average of d over the cell plus d0 of x kappa 1 over kappa 2. Okay, and similarly, we end up with the average of d dy2 a2 average over p. This is equal to, again, minus the average of d plus d0 of x kappa 2 now over kappa 1. Okay, so therefore the homogenized equation, okay, is the following: dx1 d1 dx1 u0 plus dx2 d2 dx2 u0 is equal to 0, okay, where di of x is equal to lambda I d0 of x, where we're defining lambda 1 is equal to kappa 1 over kappa 2, and lambda 2 is equal to kappa 2 over kappa 1. Okay. And again, if we look at this, right, d1 is going to be the harmonic mean of e to the, sorry, no, I mean lambda 1 is. Lambda 1 is equal to the harmonic mean of e to the alpha of y1 divided by the harmonic mean of e to the beta y2, and vice versa for lambda 2. Okay, so this should be a little bit reminiscent of what we saw in the 1D case, right? If you just take a standard mean of your diffusion coefficient, that's not going to give you an accurate approximation. If you go through the proper steps of homogenization, you find that in this case, the best way to sort of average out the microstructure is to take a harmonic mean of the modulation of your diffusion coefficient. Now that's the case in this particular problem, right? Other homogenization problems, you may come up with something different, okay? But this is maybe, you know, we went through a lot of steps to get here, but hopefully this is not too far-fetched that you just take, you know, some other kind of average is the more appropriate way to average your diffusion coefficient in this homogenization problem. Okay, so that's the last I want to say on this topic. Any questions about these homogenization approaches for elliptic problems. Okay. So let me just prime you then for what's coming up in the recorded lecture. So what I'll put up today now is homogenization of traveling waves in the bistable equation. Okay. And if you remember the bistable equation, okay, from PDE, you have some nonlinearity and a PDE. Okay, and actually, I think we dealt a little bit with it when we talked about method of multiple scales before. And we have a diffusion term here. Okay, now what's going to happen for homogenization is that an inhomogeneous problem that we might consider would be you could have an inhomogeneity in the diffusion coefficient. We're going to put an inhomogeneity, let's say, in the non-linearity. Okay. And that's going to somehow affect wave propagation. So in the homogeneous problem, right, we've looked at this before. You have these traveling wave solutions, right? And you have a stable sort of upstate that invades a stable sort of downstate here, okay? So if you have some region of your domain where the variable u is large enough, that will start to spread out over time. So this is a nice model of many systems, okay, where you have some sort of activation, right? Whether it's population growth, whether it's spread of epidemics, whether it's the spread of electrical activity in heart cells or nerve cells, okay? It's a nice canonical model of that, right? Once you introduce some sort of inhomogeneity, right? And you could imagine maybe that you also put in some d of x over epsilon here. Maybe you have some microstructure as well, right? This can happen in media, let's say, that's made up of discreteness, right? So if you're looking at maybe the spread of an epidemic across cities or something like that, and let's assume it's many, many years ago when people could only walk or something like that. There's no cars or airplanes or something like that. There's barren land in between the cities, and that means that it's harder for there to be diffusion across that barren land in that case, right? So this diffusion could mean that it's more difficult, sort of slower diffusion across here, and that you would maybe have fast diffusion inside of a city, right? Or this can happen in electrically coupled cells in the heart, right? Within a single heart cell, it's easy for things to be conducted around, but across the walls between heart cells, you slow diffusion down, okay? And the idea then is that if you have a system like this, okay, where you have sort of slow diffusion here, right, and fast diffusion otherwise, then you can have it so that it gets harder to sort of propagate across these gaps here. And so that's going to essentially slow the speed of traveling wave, okay, and even cause propagation failure, right? So I don't have to tell you it, this is the idea of sort of setting up preventative measures to prevent the spread of epidemics, right? Or building walls or reinforcements, against water waves, in seaside towns or something like that. Okay, if you make it harder for something to diffuse, and diffusion is the main mechanism by which you get propagation, if you slow the diffusion enough, then you will eventually get propagation failure. Okay, and the wave essentially will become a standing wave. Okay, so there's no more propagation here, and you get some sort of standing wave. Okay, and that's can be bad in some cases, and it can be good in others. But that's what the video that I'll post will explore. Okay. All right. Any questions about that? All right. Well, I'll post that, and then if you want to check in on Friday, you're welcome to come in for office hours if you want to discuss your project. I should have the homework graded probably sometime today or tomorrow, and then we'll be back to like just a regular lecture on Monday. So I'll sort of finish off the week with a few research examples. Okay. All right. Well, have a good rest of your day, and see you later.
Thanks, Zach.
Yep.